Log on, tune in, find out. Another good idea from Cambridge.
A great pleasure to introduce the final speaker in the Algebraic Lie Theory seminar series, Tomoyuki Arakawa from Nara Women's University, who will tell us about chiral differential operators on flag manifolds and Kac-Moody algebras at the critical level.
Thank you very much. First of all, I'd like to thank the organizers for inviting me here, this wonderful place, and for giving me a chance, giving this opportunity to give a talk. My talk will be based on the two joint works with Chepotarov and Malkov, and with Malkov. And I start with the following theorem of Beilinson-Bernstein, which I think everyone knows, but so G be a simple the algebra over C and U G V, it's enveloping algebra. Then we have a natural map from UG to the gamma x dx, where x is a variety of Borel subalgebras in G, and dx is a sheaf of differential operators on x. And the theorem says this map factors through U0G, which is a quotient of UG over the ideal generated by the positive part of the center. So here the G is the center of UG, and this is not only factor through this algebra, but this gives isomorphism of algebra. And this theorem is very, very important because this theorem, together with the cohomology vanishing, gives the so-called Beilinson-Bernstein correspondence, which gives equivalence of categories between U0, G module, a finitely generated U0G module with the category of coherent sheaves, coherent dx modules, which so the inverse factor is easy. It just given by the taking global section, and the factor in this way is given by this localization factor. And this is, of course, a theorem which everyone knows. But today I want to talk about a certain chiralization of this theorem. So what is chiralization? So I'll be using a language of vertex algebras. So if we graded vertex algebra is given. So this is a funny little thing. This is a vector space together with certain algebra structure. But this is not algebra, but usual sense. But one can associate a so-called Zoo's algebra, which is a usual associative, unitary associative algebra. And one can consider this vertex algebra as a certain affinization of this associative algebra, which means the theorem of Zoo states that there is a one-to-one correspondence between graded simple V modules and with simple Zoo V modules, which sends M to M top, where M top is a top part with respect to the grading. So this kind of highest order module, and we take just the top part of this V module. The statement that I didn't define this algebra, but the statement is that this algebra naturally act on this, and if this is irreducible, this is irreducible over this Zoo's algebra. And the inverse correspondence is given by taking the unique simple quotient of Varma module with highest weight E. So there's a certain induction factor from Zoo's algebra to the V modules. And we say V vertex algebra V is a chiralization of algebra if its Zoo's algebra is isomorphic to A. So I'm not stating that anything about. I'm not stating that the chiralization of algebra is unique or something like that. But we want something natural chiralization of a certain of a given algebra. So I don't want to define vertex algebra or Zoo's algebra because they don't give us anything. But I just want to give you some idea what this is all about by showing some examples. And so our favorite example is Kac-Moody, non-twisted Kac-Moody algebra associated with G. And if K is a complex number, there's a special induced module which I denote by V upper K, which is just induced from one-dimensional subalgebra of this one-dimensional representation of this subalgebra. So K is a one-dimensional space which K acts by as a multiplication by K, and other elements acts trivially. So this is isomorphic to U, G, T, inverse as a vector space. And this is naturally a vertex algebra so I didn't say anything, but for a vertex algebra, there's a so-called state field correspondence, and the state field correspondence is given by this formula. Here, one is 1/10 which we call a vacuum, and other field corresponding to other elements is uniquely determined by this formula. And so there's a notion of a module of a vertex algebra, and the module of this vertex algebra is essentially the same as module over G hat at level K. Level K means KK acts by small k. And in this case, it's Zoo's algebra. So Zoo's algebra Vk is isomorphic to the universal enveloping algebra of G. And the Vama module here, I wrote here, is just induced module, induced from G module in most natural way. Here E is considered as a GT, this module of this algebra by letting K act by small k, and positive part acts as 0. So there's nothing so much interesting here, but I think this example give you some idea about Zoo's algebra, because algebra is affinization of finite dimensional real algebra G, and Zoo's algebra Vk is isomorphic to UG. Just means that G hat is affinization of G, and I'm in particularly interested in the case of the critical level, where K is minus H, where H is the dual Coxeter number of G. And in this case, I write V cre G for V minus H, and this special thing happens in this case. What is special that this vertex algebra has a large center, which is called a Fagin-Frenkel center. Center in a vertical algebra sense is that this is spanned by elements P whose Fourier coefficient commutes with everything. So I'm using notation that the field corresponding to an element P is written as by this in this way. So this Fourier coefficient of the field which corresponds to P. And it's easy to see this is a vertex, a subalgebra of this vertex algebra. And so one can talk about those algebra of this vertex algebra. This is a commutative vertex algebra. And this is generated, it is known that generated by fields P1, generated by elements P1 to PL, where L is rank of G. So this means that the Fourier coefficient generates the center by acting vacuum. And the fact is that the Zuz algebra of this commutative vertex algebra is isomorphic to the center of the universal enveloping algebra. So Feigin-Frankel center is a chiralization of usual center. Now, there was nothing interesting about this vertex algebra, but the fact is that this algebra is not irreducible, and one can consider its irreducible quotient, the unique simple graded graded quotient of Vk, which is again a vertex algebra. So this is because the so Vk module is the same as a module over G hat. This is a irreducible module of affine Lie algebra. So I might restrict myself to the critical level case only. And this is usually written as L minus Hx lambda 0. This is a irreducible module, highest weight, irreducible highest weight module with the highest L minus Hx lambda 0 in the usual notation. And this actually is easy to describe. I mean, it was proved by Frankel, Gatsgory, that the maximal submodule of this maximal submodule of this highest module is generated by the center. So this is a quotient of Guicry by the element which generated by a submodule generated by the center. So the space spanned by these elements. So I. And from this, one can show that the Zuz algebra of this vertex algebra is also a quotient of UG by the center, and actually it's exactly the quotient of the center. So Zuz algebra of this vertex algebra isomorphic to U0. G, which is a quotient of UG by the positive part of the center. So we have here a chiralization of this algebra. So I want to now talk about the chiralization of the right-hand side. So in order to do that, I need to explain so-called beta gamma system in physics. So let A hat n be algebra generated by this element where y is moves from 1 to n and n moves over G with the relation A I M B J n equals to delta I J delta n plus M0. So this is a simple algebra, and I denote by Fn the irreducible representation generated by vector 1, which satisfies this highest weight condition. So AI to this is 0 for n is equal greater than 0, and Bi n 1 equals 0 if n is strictly greater than 0. And it is known this is naturally a vertex algebra by assigning a I minus 1 to 1 a field G, which is just a I n z minus n minus 1, and field corresponding to Bi 0, 1 G is Bz. So this element, this field generates this vector space, or vertex algebra. And from definition, I mean, as you can easily guess, the Zuz algebra of this vertex algebra is just a wild algebra of degree n. So Zuz algebra of Fn is isomorphic, which I denote by An. So this is a subalgebra of A hat n generated by the zero mode of this algebra. So this algebra is kind of zero mode algebra of a vertex algebra. And so because this is a very simple algebra, its representation theory is very simple. So in fact, there's an equivalence of a category between this wild algebra, Zuz algebra, with this a suitable category of this vertex algebra. So I consider graded category of graded module of the vertex algebra. So which is given by sending E to the induced module from induced from E. So this is the subalgebra generated by the positive part of the algebra. And so because dx is locally algebra, to consider chiralization of dx, you just have to glue this vertex algebra by in a natural way. So as a result, we get sheaf of chiral differential operators on X, which is locally isomorphic to Fn. So this is a sheaf of vertex algebra, sheaf of graded vertex algebras. So this is a sheaf of graded vertex algebras on X, locally isomorphic to Fn. So I'm considering now flag variety. So it has a covering which is also isomorphic to affine space. And so the section on UW is isomorphic to Fn. I don't want to explain this sheaf in detail, but I do explain some properties. So first, this is a graded vertex algebra, and its top part is isomorphic to the structure sheaf of X. And second, for dx is generated by dx zeroth part and degree 1 part, and degree 1 part as vertex algebras. And as for degree 1 part, we have the following exact sequence of sheaves. And what is the most important thing is this is locally just a beta gamma system. The category of module of this vertex algebra is equivalent to the category of dx module. And the correspondence is just given by locally considering induction factor. So but so this is existence is non-trivial, but it was shown that there is such a sheaf on a flag variety. But one remark is that although it contains a structure sheaf as a top part, this sheaf is not an OX module, because zeroth part multiplication of zeroth part is not the same as the multiplication of zeroth part. But there exists a filtration such that corresponding graded sheaf, which is also decompose with in this way, and each of these are locally free of finite free OX module of finite rank. So one can consider dx chi as a certain deformation of an infinite dimensional vector bundle. Now, so we had a map from UG to this global section, and in the same way we have a natural homomorphism from V crit to this global section of sheaf of chiral differential operators. And the level has to be critical, and such that it's locally isomorphic to restricted Wakimoto modules. Restricted means its Frenkel center has a central character. And the statement is that this gives isomorphism from V under crit to Vx dx. Right. So this is a simple module as a critical level, and so the statement means that the global section is a simple vertex algebra. And so this is a kind of chiralization of Borel-Bell theorem. And one can do the similar things for other modules, for other in GG integrable modules. So let lambda be dominant weight of G. And we have the corresponding central character. So it's the evaluation at the reducible finite dimensional representation E lambda with highest weight lambda and corresponding quotient algebra. And there's a notion of TDO, twisted differential operators on X, which gives equivalence of the so there's a twisted version of the equivalence over there. So there's an equivalence from U lambda G mod with D lambda mod. So this is so-called TDO, which assign E lambda to certain the invertible sheaf corresponding to lambda. So the lambda is twisted by this invertible sheaf. So the lambda is L lambda tensor dx tensor L lambda inverse. And we can also consider the chiralization of this twisted modules, and which is equivalent to this category in the same as non-twisted case. So there's a subtle point that this is not vertex algebra anymore, but one can consider the universal version of TDO, and one can one can do parallelize to the universal ones, and one can consider this as a module over the universal chiral differential, twisted chiral differential operators. But I don't think I explain it in detail. So anyway, we have the corresponding object here, so which I put L hat. So in general, we have an object here and localization, and corresponding object I denote by putting hat on the above. And also, by taking global section functor, you get a module over as a critical level over fine D algebra. And the statement is that we have the similar things. So for any dominant dominant integral weight, this global section is isomorphic to the irreducible module of a fine D algebra with highest weight lambda hat, where lambda hat is just a weight corresponding to lambda. So one can consider this sheaf as a localization of this irreducible representation. And one can, I didn't say, but one can consider the chi as a localization of this simple vertex algebra. But as you can see from this diagram, this functor cannot give equivalence of categories as Benson-Bernstein cases, because if this is equivalent, this means this is equivalent to the category of G module. So in particular, we don't have the cohomology vanishing of this global section functor. But because this correspondence is equivalence and this correspondence is equivalence, so so if we, by considering Euler character, the convolution functor gives a map between characters. So it's easy to compute the Euler character of the corresponding sheaf. So the Euler character has following form. So W is a while group of G, no, not G hat, but this is a root system of G hat. And one of the interesting things is that the specialization in particular if we consider the zero weight, the specialization specialization means a homogeneous specialization. A specialization gives elliptic genus of our flag variety, because Chiral differential, one of the main applications of Chiral differential operator is a computation of elliptic genus. And so this is our first statement. This is infinity. Finite. And what is more interesting is that we don't have cohomology vanishing here, but we can compute each higher cohomologies. And the result is the following. So this is again a module of a affine linear algebra as a critical level. And this is a direct sum of the same module, but with a degree shift. So this is again a finite while group. So this means that the character of this cohomology is a product of character of L lambda hat plus this a degree shift part. So where QQ equals E2 minus delta. Sorry. Thank you very much. So, no, X is finite flag value. Still finite. No, we are considering Chiral differential operator, which can be so we have two ways of expressing Euler characters. So we have these groups are different. So we have two expressions. So combining these two, we get this equality. And it is well known that this part can be expressed by the product of a root system. So as a result, this gives the character formula of L lambda hat. So as a result, we get this explicit character formula of L lambda hat. still have time, so I'll make some comment about this theorem. So first of all, it's easy. I mean, this each cohomology is an object of so G T in integrable G hat module as a critical level. Which admits central characters. So the integrability of G follows from the fact that X is a projective variety, and we have the filtration whose a graded associated graded thing is a direct sum of locally free OX modulo of finite rank, and the fact that it admits central character with respect to the Fagin-Frenkel center follows from that it's locally just it gives restricted Wakimoto modules, and it is known that this category is semi-simple. So we know that each cohomology is a direct sum of simple modules. So we just had to compute the multiplicity. And to compute multiplicity, we consider this chiralization idea. So I'm commenting on some on our on the proof. And so we have so-called the resolution. So this is a dual of VGG resolution, or Kampf's resolution. So each Ci is a direct sum of a dual of Wama module of G and because localization gives equivalence, we have corresponding. So this is a category of G modules, and we have corresponding. Is a sequence of sheaves. And because chiralization procedure is exact, we have corresponding exact sequence. And this is our Ilhat lambda. And the fact which one can prove is so the fact is that we have the delta ham to lambda localization of dual of one module is acyclic, which is easy to see, and the fact is, so this is acyclic, and this is actually isomorphic to the dual of restricted Vava modules. So this is dual of restricted Vava module. So this is largest submodule of in the dual of Vama module, which admits a central character. So because this is acyclic, we just have to compute the corresponding sequence this gives. So HI is isomorphic to a cohomology of the complex of this form. And to compute this cohomology of this complex, one can use the technique of the B-aristic cohomology, which I don't think I don't want to explain, but one can use the so-called Drinfeld-Sokolov reduction cohomology functor to compute this cohomology, and we get this nice formula. It's early, but this is what I want to talk.
So in the classical valence and Bernstein situation, I mean, there are some things that are easier to say in the language of perverse sheaves. Is there?
I don't know. But so the category is equivalent to the dx model. So in that sense, it's
so
nothing interesting.
Okay. So there's no sort of extra information you can get about these cohomologies or anything like that.
But we do get elliptic genus by computing Urakel. But in that sense, it might be something interesting. But I don't know.
Any other questions?